Okay, welcome. I'm going to do this lesson for all three of my classes, and you can go to Schoology to get the notes and the worksheet that you're going to be doing, or you can stay here in School Tool. I'm sorry, stay here in OneNote, and there are two sheets in your Notes tab, and there's going to be one thing in your Handouts tab, and they are all to be done before you leave or before you leave class today. All right, so I'm going to get started. What is molecular polarity? Why is it important? And where can I find polar molecules in everyday life? Well, molecular polarity is a little different than what we've talked about before, and we talked about what is called polar bonds. Polar bonds are going to be between a metal and a nonmetal, where one of them has a much larger electronegativity than the other one. And by the way, you look that up on table S. Two nonmetals, one of them has a much higher electronegativity than the other. And as a result, you end up with a type of bond called a polar covalent bond, where the electrons are being shared unevenly. Because chlorine is so much more electronegative, it actually pulls the electron more than hydrogen does. So chlorine ends up getting the electron most of the time, and as a result, it becomes slightly negative, whereas the hydrogen becomes slightly positive. Why is it important? Because polar molecules are all over the place. They're inside of our bodies. We're made of them. Proteins, DNA, they all rely on polar bonds. And where can I find them in everyday life? Well, the most important thing is going to be in water. Water is a polar covalent bond, and it is a polar molecule, and I'm going to explain that for you right now. It says to first draw the Lewis dot diagram for nitrogen, and if you remember that, nitrogen is one of the diatomics, and it looks like this. Each nitrogen has 5 valence electrons, and it says how many single bonds are present. I'm going to highlight them in green. There's a single bond here, a single bond here, and a single bond here. So we would say that there was 3 single bonds. Is one element more electronegative than the other? No, they're both the same element, so they have the same electronegativity. So the answer to that is no. It says if no, move to part D. If yes, then you have to determine whether or not something is going to be slightly positive or slightly negative. So we're going to skip that and go on to D. Does this molecule have a polar or a non-polar bond? And of course, that's going to be a non-polar covalent bond. Because they're the same exact element, they're going to share their electrons 50-50, and it's an equal sharing of electrons. So we call that a non-polar covalent bond. Remember, polar means that there's a positive side and a negative side. So because they're both exactly the same element, they would not pull the electrons further one way than they would the other. Then it says, ask yourself, is the molecule symmetrical? Well, that's a new term. The word symmetrical means that you can cut the molecule both horizontally and vertically, and it would be the same in all directions. Let me show you the first one. If you were to take this molecule, I'm going to do this in black, and cut the molecule in half, literally cut it in half, and then fold the bottom part up onto the top part, they would be mirror images of each other. They would be the same exact molecule. And if you do the same thing from top to bottom vertically, the left side and the right side are the same. So we would say that would be symmetrical. It's kind of like the human body. The human body has symmetry only in one direction. If you cut the human body vertically, the left side of the body and the right side of the body are exactly the same. But if you cut it horizontally, obviously it's not. I have the head on the top and I have the feet on the bottom, so they are not mirror images. So we would call the human body asymmetrical. Okay, asymmetrical means that you cannot cut it evenly. So we say that that's a yes. So then it says, is this molecule polar or nonpolar? Well, in order to be a polar molecule, in order for a molecule to be classified as polar, it needs to have two conditions. The first condition is it needs to have a polar covalent bond, and the second condition, is that it has to be asymmetrical. So let's go to the first one. The first one says, what type of bond does this have? And it's right here highlighted in yellow, nonpolar covalent. So that means that this would be a no. So that immediately tells you that it's a nonpolar molecule. So this is a nonpolar molecule with nonpolar covalent bonds. And then it says, highlighted here in green, that all diatomic molecules are the same way. Iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. They all do the same exact thing. The next one would be carbon dioxide. So I'll do this one in baby blue. Carbon is going to look like this. It's kind of one of those odd ones. Oxygen has 6 valence electrons, so it looks a little bit like that. And how many bonds? I see 2 double bonds. I'm going to highlight them in orange. 1, 2, 3, 4. So I see 2 sets of double bonds. Is one element more electronegative than the other? And the answer to that is yes. Carbon has an electronegativity of 2.4, where oxygen's 3.5. So that means there's going to be a charge distribution towards the oxygen side for both molecules, or for both oxygens. So there's going to be an uneven charge distribution. So the answer to that was yes. It says, if yes, label positive and negative. That means that oxygen is going to become slightly negative on both sides, and then carbon is going to become slightly positive. Does this molecule have polar or nonpolar bonds? Because the bonds have such a difference in electronegativity, we would say that they were polar bonds. And then ask yourself, is the molecule symmetrical? Again, back to black. Cut this in half. Is the left side and the right side the same? Yes. Cut it horizontally. Is the top side and the bottom side the same? Yes. So you would say yes. Is this a polar molecule or a nonpolar molecule? Again, this would be nonpolar. Why? Because if it's a polar molecule, you have to have 2 criteria. 1, a polar covalent bond, and then 2, it needs to be asymmetrical. So look at the rules that we just listed here. It says here, what type of bond is present? Polar. Okay, so that takes care of this criteria, but it has to be asymmetrical. This right here says, yes, it's symmetrical. So this criteria is not met. So if it's not met, then that means it's not a polar molecule. So this is a non-polar molecule with polar covalent bonds. On to the most important one. Oxygen, again, looks like this. And then it's going to bond with hydrogen like that. And it looks to me like I have 2 single bonds. I have one here and one here. Is one element more electronegative? Yes. Again, you get that from table S. You have to look them up. You have to look up their electronegativities. I might even suggest looking them up and writing them down. So that means the charge distribution is going to be like this. So that means oxygen is going to be negative and each hydrogen is going to be positive. Does this molecule have a polar or a non-polar bond? It's going to be polar because the electronegativities are different. Is it asymmetrical? Let's look and see if it's symmetrical. Cut it this way. Is the left side and the right side the same? No. Cut it this way. Is the top and the bottom the same? No. So that means it's asymmetrical. It's asymmetrical. So then, is this molecule polar or nonpolar? We would say that this one would indeed be polar, because I have a polar covalent bond, highlighted here in black, and it's asymmetrical. So we would say that this is a polar covalent bond. I'm sorry, we would say that was a polar molecule because it's made with polar covalent bonds. Okay, I'm going to let you do number 4 and number 5 and number 6 on your own. Do the best you can. And if you have any questions, fire them off to me and I'll do the best I can at answering them. Okay?